Alrighty, so I'm hoping that this weekend I can get a lot of grading done for lots of courses, so I'll be able to give you some feedback on some of the stuff that we've had you turn in. Yesterday I added a homework due Saturday night. Yeah, why not? And that homework is just the idea that this linear programming structure is very flexible, really. You can take a lot of different things, a lot of different mathematical forms, and actually linearize them pretty well in different ways. I will give you a hint on one of those homework problems is that suppose I want to minimize or maximize something, right? So if I want to minimize or maximize, okay, some function, f of x. Okay, a big hint here is that if g of x is monotone, ooh, there's a big word, monotone. What the heck is it? Monotone function? What the heck does that mean? It never has inflections in it when it speaks? No? Yeah, a monotone function is one that's always, now, I'm going to say always increasing or always decreasing. Now, that's not quite right. That would be strictly monotone. Monotone, well, it could go flat for a while. Okay, so usually the types of functions we deal with, that wouldn't really happen much. But you could have, if you think of something like x cubed, that's monotone, yet there is one spot right at 0 where its derivative is 0, so it's not increasing right there. Okay, but it's not decreasing either. So it's always increasing or maybe has a derivative of 0. Or it's always decreasing with maybe a derivative of 0 in there somewhere. So if g of x is monotone, then we can also, or well, not also, we can use g of f of x in place of f of x. Okay, now why would that be? Well, so now you got to be, let's see, I think you have to be a little careful here with min and max and so forth. But so suppose I want to maximize f of x, right? Maybe f of x looks like that. Okay. Now though, if g of x looks like this, I just made it linear. It doesn't have to be linear, but it's always increasing, right? Then what that says is a bigger x makes a bigger g of x. Okay? Oh, well, so if I'm looking at g of f of x, a bigger f of x makes a bigger g of x. Right? Under this situation, what we have is that g of f of x1 is less than or equal to g of f of x2 if f of x1 is less than or equal to f of x2. Right? So when you've got this situation, right, I can just maximize g of f of x instead of f of x. Because it's the same idea. Now, where that can come in really handy are things like, right, usually now we're doing linear programming and so forth, so we're trying to make everything linear. But in general, if I want to maximize a function, what do we think of from Calculus 1? What do you do to maximize a function, to find where the maximum is? Right? Well, what do you notice here at this maximum? Right, it peaks. So what's the derivative right here at the maximum? 0. You look for where the derivative is 0. Okay? Well, so suppose I'm dealing with a function like the square root of x1 plus x2. That's actually one of your homework type problems, I think. And say I want to maximize that. Right? Well, can't I just stick that into the squaring function and get rid of that darn square root? Right? You know, would you rather deal with the derivative of that or the derivative of that? I think that one. Right? And so that's where this comes in is, well, if I want to maximize the square root of x1 plus x2, that's going to occur at exactly the same x1 and x2 as the maximum of this. Okay, because what did I do? I squared it. And so if that's bigger in there, that's got to be bigger because the x squared function is an increasing function. And if it were a minimization originally, that's okay. You know, I could still have an increasing function with a minimization. Right, because, well, if it's smaller, I just want it smaller. Okay, but the key is that that function is monotone. But we have lots of monotone functions. You know, any of the power functions, and that's the nice thing is, okay, this is a square root. But what if it was to the 3/2, right? Or well, better yet, 2/3 or something like that. Well, who cares? 2/3. Take it to the 3/2. Because x to the 3/2 is a monotone function. Okay, so I can undo things when I'm dealing with an objective function that I want to maximize or minimize. I can often change it to a different function where the value, absolutely the value is going to be different, right? If this is 1 and that's 1, here inside there I get the square root of 2. Well, here I get 2. Very different values. But the x1 and the x2 are exactly the same place. So if I can find them, well, I can always go back here and tell you what the square root of their sum was. It's the finding the maximum that's the hard part. It's not evaluating the function once you're done. And so, you know, these kinds of things, you know, and so, you know, stuff like that is a good idea. Now, one of the problems I give you is a product. And so if you have f of x times g of x, can you think of a function that would turn a product into a sum? Can you think of a function that turns a sum into a product? That one you're a little more likely to, I think, come up with. And this is, this is one of the things in this kind of stuff with modeling. This is what I think adds to just your mathematical strategies and comfort and strengths and so forth, is that, well, I just got through yesterday telling calculus, and I think I've probably said it in here before already this semester. All math is applied. I think I've said that, maybe not, I don't know. But all math is applied, because you'll hear people, oh, I like applied math or I like theoretical math. No, all math is applied math. And actually, all math is theoretical math. The thing is, what's the difference? I mean, because I would agree those are perfectly good labels to kind of discuss areas of mathematics. Theoretical math, as we tend to think of it, the stuff we do in it and so forth, like you tend to prove existence of things in theoretical math, like the solution exists, or things like about the derivative, that if I have a nice smooth function, its derivative will be 0 at a relative max or min. That's a theoretical thing, right? I didn't schedule an airline with that. And but it's very applied in the sense that what I've done with that theory is I've just made a great tool for an applied mathematician. And so it's applied, but what's it applied to? More mathematics. And so my analogy is with engineers. You can be an engineer who builds bridges, who builds cars, who builds, whatever. Actually makes products that people use on a consumer basis or even company basis, maybe. Or you can be the engineer who makes the machines that sit on the assembly line to make cars. Theoretical, now, everybody would call the engineers all applied, right? But I'll go, theoretical engineer is making the tool that sits on the assembly line. The applied engineer is making the car that uses that tool. And so it's the same thing in math, and in that way, I think when because some of what we do in the math modeling is you really have to start thinking about functions and property and structures of things, and just like a system of equations. What the heck is that, actually? And it turns out it really helps to understand what that is in the modeling process. Well, but by thinking about that, it also makes you stronger in the theory. And vice versa, if you know those structures really well, and you know properties of functions just in general and so forth, those are theoretical things. But they can make you a much stronger modeler. And so, we want to kind of remember all that. But now, so back to a function that turns a sum into a product. exponential functions, if I have a sum and I place them inside an exponential function, I can actually think of it as a product. So, if I want to do the opposite of that, what function maybe comes to mind? Because I want to do the opposite. Yeah, right? So, you know, that's natural log function has that beautiful property that if I take the natural log of a product, I can actually do the sum of the natural logs. Oh, yeah, that's nice. And so, you know, that's part of the, you know, that can be used as part of the homework. All righty. So today, I guess I want to talk about networks. I thought about it a bit, and I decided to add a chapter in there. So I will say, you know, when you look at the instructional content, on the surface, it looks like I've given you way, way too much. I mean, I would agree with that. You know, if I looked at that and, you know, some teacher said, oh, this is what we're doing, and I looked at that, I would go, whoa, wait a minute, that's too much stuff. There's too much volume of things there. Okay? So I recognize that, and it's not too much stuff because we're not going into all the solution process of it. So what's happening in chapters 5 and 6 is they are introducing some processes or concepts or structures that one could model using networks. But then they're giving us algorithms for each and every network type of problem. Well, we wouldn't solve them that way anyway in this class. We're just going to give it to technology. So all we really care about in those sections is I want you to realize the applications. And really, these are all applications of linear programming. Okay, so what we want you to see, though, is that if I have a problem that, you know, if I can structure a problem as a network, I may be able to use linear programming. And it turns out that it's really nice. I mean, it ends up giving really nice answers. It's, again, one of these theoretical things that it turns out. But so, you know, let's just, and that's why I decided to add chapter 5, was it just gives us more types of problems to just realize we can solve. And so this is actually the end of chapter 5. But to me, it seems like it's sort of the simplest, most straightforward problem that they give in all of this. And that's the assignment problem. And let me switch over to here and make that bigger. Bigger yet, maybe. There we go. Okay, so this is, I guess, page 178 in chapter 5. And here, they're just looking at a basic problem of assigning jobs to machines. And actually, when I was at Albion College, I had a student who went to a caster plant. It's kind of a strange thing that the town, this small town, Albion, Michigan, is sort of the caster center of the world or something, or at least of the U.S. And all because, you know, one caster company started there, and then there have been some spin-offs. You know, people get upset and leave the company, start their own company, or they just decide to try their own company or something like that. And so there are these caster companies, and actually my doctor started taking over his dad's caster company and left the medical profession, and we were friends, and so I had a student looking for something to do, and so she went to look at exactly this sort of problem. Okay, you have different things that have to be done. In their case, they had different size casters, different types of casters that had to be made, and they were made on lathes. They call them CNC, computer numeric control lathes, CNC lathes. But each lathe, you know, it would take a different amount of time, so that's a different cost. And of course, the machine itself costs something different, and they amortize that. I don't know how they did all that, but you know, but there were different time costs to making the different products on different lathes. And so the question would be, well, okay, what should I assign to what? And here in the simplest case, it is simply, I want to assign one job to one machine, period. I have 3 jobs, I have 3 machines, I want to assign them. What's the cheapest way to do it? And they give an algorithm to do this, but once you set it up as a linear program, you can just solve it in something like Python on our Sage cell, and we'll do that today. And so as you look at this, right, what we want to do on this particular problem, so this is the assigning jobs to machines. Okay, so this is what we want to do. Well, as you look at this problem, the objective is to, in this case, minimize cost. Pretty straightforward. We want to minimize cost. And then as we think about constraints, well, typically, and you think about something like turning an item on a lathe or something along those lines, yeah, pretty much you have to assign one job to one machine. Now, you could make things much more complicated by saying, well, you know, actually, we can wait, and so we could assign 2 jobs to the same machine, but they can't get done at the same time. It would take time. Oh, yeah, you can ask that kind of problem. It just starts getting harder and harder. Okay, so we're keeping it as simple. Is each machine can only get one job. Each job can only go to one machine. And that's what we want to do. So each machine only one job, and each job, only one machine. Now, so here's everything. This is all I need as far as kind of setting up my structure. But in order to make a linear programming problem, I need variables. What's going to change? So when you start thinking about variables, what is it that you are changing? What do you have? Whoops. I got to come back here. Sorry. I'm apologizing to whoever might watch this. Okay? Because I had that showing. So I'll just recap. So we're looking at that. We need to assign jobs to machines. Our objective is to minimize the cost. We said that. Each machine only one job. Each job only one machine. And so now we need a variable. What is it we have a decision over? Well, we can decide which machine takes which job, or which job goes to which machine. And let's see, how did I say it here? So I said, okay, I got a variable x, and I'm going to put two subscripts on it. Like 1 and a. And the idea here is this is going to equal 0. Well, actually, let's go 1. It's easier to state it this way. 1 if job 1 is assigned to machine A. And 0 otherwise. So if it's not. Does that seem reasonable? Right? That's what I can decide on. And it really is just, it's sort of an on-off. Either I assigned it to that, or I didn't. And so, okay, 1, 0, that seems reasonable. Now, I could use any values I wanted. I could use pi if it was assigned, and e if it's not. Okay, but if that's what I choose, I'll probably find it's really hard to then describe the situation mathematically. So a lot of it is, why 0, 1? Well, because when you've seen what other people have done and then you've done some things for a while, you just realize, oh yeah, that's way easier. So that's what we want to do for each of these, right? So we'll do this. We'll have variables xij like this, where I can equal 1, 2, and 3, and j can equal a, b, c. And then I don't need any other ones. And this kind of describes everything. Any questions at this point on this? My guess is it seems pretty straightforward. It always seems pretty straightforward when the teacher's talking about it. It's just one of those things. But okay. So now we have to describe our constraints and our objective. Well, the objective really isn't bad at all. I think the objective, it's just the cost of our decisions. And so here, what I want to do is minimize z, say, equals And I just go through those numbers. Now, they aren't up there, but I've got them right here. So I need to minimize, well, okay, actually, we ought to consider something. We ought to think about something before we really start writing stuff down haphazardly. I had already considered that, so I wasn't thinking about it. We need to organize this stuff, because see, for you and me to just write something down, a double subscript really doesn't bother us much. I mean, it might bother us a little bit, but you know, we get more and more used to it as we see it more. But yeah, so you know, it's not that big a deal, but oh, if we're going to use technology to solve it, oh, it could bother that a lot. So we have to think about how we're actually going to do these variables. And the way I did it, you could choose one of the two, I think, that would make sense. Either kind of go through each job one at a time. So I've got job 1 goes to machine A, B, C. Job 2 goes to machine A, B, C. Job 3 goes to machine A, B, C, and order things that way. So your actual first variable, if you change the names to like Y1 or Y2 or something like that, that you'd know how to map them out, you know, what meant what. Because when we give this to Python and Sage Cell, it really just sort of thinks of the variables as, well, actually, it thinks of them as starting at the number 0. 0, 1, 2, 3, 4, 5, and so forth. It doesn't do the double subscript thing. You know, you can't, you don't give it to it that way. And so, you know, you want to think about that. And so you can either go, you know, 1 ABC, 2 ABC, 3 ABC, or A, 1, 2, 3, B, 1, 2, 3. Yeah. Seems like, you know, if I could sing, I'd start doing Michael Jackson or something, and Jackson 5 and all that stuff. But I don't sing so well. I have plenty of witnesses to attest to that, so I won't do it. All right, so we'll do it that way. We'll start with the 1 and the ABC and so forth. So if we do that, we end up with the numbers 57 x1a plus 42 x1b plus 65 x1c plus, where am I, 39 x2a plus 48 x2b plus 46 x2c plus, and then 43 x3a, 72 x3b, and 53 x3c. Okay, so we have all those, and we'll put them in that order. And then, now, each job exactly once. Okay, each job exactly once. Well, my variables on whether I use a job or not, right? They are just the xi, a, and x, you know, or x1a and so forth. So, if I were to sum up all the x1s, I should get 1. Does that make sense? Right? One job. If I get anything other than 1, I either have tried to assign too many machines to that job, So I'm trying to put that job on more than one machine. I'm not doing the job exactly once. I'm doing it more than once. Or if it's less than one, well, I haven't done the job. So here we have something like, x1a plus x1b plus x1c. And I'm going to go way down here and say equals 1. And then similarly for the other jobs, right? So x2a plus x2b plus x2c also has to be 1. And x3a plus x3b plus x3c has to be 1. So there's each job exactly once. And then I can do the same thing for the machines. Now, I set it up like this because this is the order that we put the variables in. And part of the reason I chose this order was this was the first thing I thought of was the jobs, one job. And so I thought of adding the ones all together. And so I thought, well, I'll put those first. But now, if you're doing exactly one machine, well, that is x1a plus x2a plus x3a is equal to 1. And then similarly for B, and this is actually nice, sort of, in that I'm running out of room. x2b plus x3b equals 1. Because as it turns out, now, neither of you have had linear algebra, have you? No. Oh, you have? Okay. You didn't have it last spring, though, right? You must have had it a year ago or something? I mean, over a year ago?
I had it last spring. No, well, not this past one. Yeah, it was a year ago.
Yeah, okay. So, what you learn in linear algebra is, it turns out if I could add that third machine in here. Actually, I don't need to. It's redundant. So from your linear algebra days, it's dependent on these other 5 equations. It doesn't add any information. So if you put that into the model, I'm pretty sure the Python doesn't really care. I mean, you could put it in and it'd be fine. Worst case is you would get an error message or something that basically said, hey, you don't need that constraint. But yeah, it turns out with this particular assignment structure, the 6th equation is not actually needed. So you can put it in, but I ran out of room, so I'm going to call that like, fate that says, yeah, we didn't need to put that in. So there's my problem almost. Now the way we have it stated, right, we would put on there xij is equal to 0 or 1. Oh, that's not good. Now, actually, I think in the Python you can, I think we can tell it integer on that. I'll have to look again. I think you can tell it integer for some of the variables. I could be wrong. But that's integer, right? I'm saying that 1/2 is no good. Here's the thing with these network problems, and notice I'm calling this a network problem. A network problem, anything where I can conceptualize it as a bunch of nodes. Okay, here's the job. here's the machine. So 1, 2, 3, 4. A, B, C, D. And in this case, you see, I've got all these relationships like this that I could go from, oh wait, are there 3 or 4? Sorry. Expanded the capacity of the company without any money. Okay, so yep, okay. So I could draw the relationship of this problem as a network. Here are the jobs, and which jobs can be done by which machines? All of them. Now, if one couldn't, well, I just erase a line and say, well, it couldn't be done by that machine. That's okay. And what we would do is we'd just take out a variable. We'd say, well, that variable doesn't exist, can't be done. And there are other ways to do it without taking out the variable. Okay, we'll maybe look at that. So this is a network problem. And it turns out that these network problems, pretty much all of them, that if I think about conservation of flow, and that conservation of flow would be whatever goes into a node needs to come out unless it's either a beginning or an ending node. If you relax this and say that your xij has to just be between 0 and 1, it works. It only gives you zeros and ones as answers. Now, you really need to take, I think, a linear programming course and do a bunch of modeling with it and so forth to realize just how amazing that is. And this is awesome. This, it's one of these mathematical structural things that if I have a network problem that I'm modeling with linear programming, I don't have to worry about the integer aspect. And the problem is, worrying about the integer aspect is hard. Now, how hard? You give it to technology, it does pretty well. But from the standpoint of algorithms and computational time and all that stuff, computational complexity we call it, it's hard. This is a hard problem. But we don't have to worry about it. And that's an amazing, amazing thing. And so, this idea, linear programming, at one point, now this is a few years ago, I haven't seen a statistic more recently, but in terms of just sort of standard modeling techniques and algorithms, it is the most widely used model in industry. Now, if you relax that a little bit and say what technique is used the most, it's actually not linear or at least wasn't then. It wasn't linear. It was simulation. We're going to be looking at simulation as well, but I wouldn't call simulation sort of a single model. Simulation is a much broader notion. And so, most widely used. I worked in industry. I used it quite a bit, as a matter of fact. Really got some nice results from using it that at least people in my company were really happy with. They were really happy with me because I had come up with some things that used this. And, not because it was linear programming, but because I got an answer for them that they believed, right? So in that way, this is just an amazing tool, but it gets harder when you do things like say, oh, I need integer answers, not a continuous possibility. But in these problems, if you set up a network problem, I don't need to do this. I can get rid of that and just say 0 is less than or equal to xij is less than or equal to 1. And that will do just fine. And the difference in computation, especially, this is a really small problem. But, you're doing something with like 10,000 variables and 1,000 constraints or something like that. Way, way better. And so, let's go back to this stuff. And I went ahead and made the model, and we'll kind of look through that. So, this is the case where I had to make sure I knew my organization of stuff. And so, those are just the coefficients, right? So here are the 50, is 57 x1a, and then 40 plus 42 x1b. So I just read them off, wrote them in. Just like that. And there are my C coefficients for this thing. Then I needed each row of constraints. And notice here I said AE. I think in the original stuff, this, and this is, of course, is where I got it, they used just A or something, and their example's probably down here somewhere. There we go. They used the upper bound stuff for this, and but they just put in each row at a time. Well, so for us, remember, our first row was the x1a, x1b, x1c. So those were just all ones in front of those. And then zeros on all the rest. And that's part of the reason I wrote it the way I did up there. I can go back here really fast and say, that's the reason I wrote them sort of this way, is those are all zeros in that area there. So so then I just went through, and it gets kind of long there, partly because I blew it up really big. But there's the end of the first 3 rows, and then I have the other 2 rows tacked on, and putting the ones in the proper places to match up with the right variables. That's where organization is important. But that's all it is. I'm just making sure I've got things in the right place. And then, so that was the equality left-hand side. And then what were they all equal to? They were all equal to 1. So I just put 1s in all of that. And then the bounds. Now here, I'm kind of showing you compare. So what I did was I just went through, well, every single one of them was 0, 1. And if you look here at what they did on their stuff, they did the square bracket, and then they had the first bound, and they wrote it out. They said this. They did that, and then they put that whole thing, x0 bounds, in here. Well, they're all the same, and I don't really need to know. I mean, I know that that's the first variable, the second variable, the third variable. I don't really need to write out all that stuff. I can just put in each of those is 0, 1. And so the lower bound is 0, the upper bound is 1. And so I put that in here for the bounds, as opposed to, this whole thing up here, right? I didn't want to type all that. Well, I did type it in so you could see, but I didn't want to type all that stuff in there. And then finally, I'm using the method simplex. I tried it without it, and it worked just fine. But that is one caveat to the getting integer solutions, is if you don't use the simplex method, you actually might not get integer solutions. And so I just tossed the simplex method on there to make sure we get integer. And so I evaluated that, I hit evaluate, and it says, hey, it terminated successfully. The value is 131, and here is my solution. And then as long as I know, as I know what order everything was in, so I see this was A1B or X1B right there, then C, and then 2A, 2B, 2C, so that was X2C, and then finally X3A. But I had to remember what matched up with what. But it's that simple. I mean, that fast, and it just does it for us, and not too bad to enter. Questions on that right now? On anything? Okay, so I'll try to post that code. Just so so you can have it. Now, and what's nice is if you do kind of skim the material as far as the algorithms and so forth in the textbook, what they'll show you is that, well, actually for the assignment problem, I don't think there's a problem. But for similar problems, the transportation problem, and I'll make some videos on some of these other problems, using those algorithms, you have to sometimes put in dummy variables and so forth for things. But in this case, no, you don't have to. And one thing I just wanted to look at was, it'll make it a pretty simple problem, but suppose we actually only had 2 jobs, but we had 3 machines. Right? 2 jobs, 3 machines. Then there are a couple ways we could handle it. Is if one is just get rid of those extra variables, right? And that's probably what I'd do if I was just starting at the beginning. But from a modeling point of view, another thing I could probably do is I could go in here and say, well, to put anything on, or to schedule job 3 is just going to be really, really expensive. Well, so in a way, the mathematics is going to say, well, that's the last thing it's going to worry about. And if I make it exactly the same on every machine, then it doesn't care, the mathematics really doesn't care which one I assign it to. So if all of a sudden, if I had this big model in there, and you all of a sudden came to me and said, oh, as it turns out, we don't want to do job number 3. Well, I could go through and I could pull out those variables, right? But that sounds like a lot more work than what I just did. So I know that's the last thing it wants to schedule, but it will because I'm making it schedule. But it doesn't matter which one I assign it to. And so I think from an intuition standpoint, just make it really expensive. And so, I can do that, and we can look at an answer. And it says, terminated successfully. It's now 1,081. But actually, if everything costs the same on doing that job, did it really need to be 1,000? Could it have just been 0? right? So look at the solution, right? It's 1,081, and so if it had been 0, it'll be 81. And it says that we should, schedule the first 2 jobs with machine A and B. Really, machine B and A in that order. But so, go back up here, and what if I had just done those as zeros? And I don't think that hits the intuition as fast that, oh yeah, I can just make them all 0. And I evaluate that. Now I get my value of 81, and I do get the same solution. Because again, having all those values the same, it didn't matter whether they were 1,000 or 0. Oh, make them 0, so then that doesn't mess up my objective function in the end. And so that's really a lot of the modeling, but that's also theory, right? The theory saying that if every cost is exactly the same, then the mathematics will not care. Okay. All righty. So that definitely takes us to the end, and so I have that other homework for you to work on. I should get your project to you reasonably soon. I would say, like, hopefully by tomorrow night, get that project. The project is, it's a real life problem that somebody in industry wanted solved, and it turned out to have some really nice aspects to it. And I will take you through my solution process. How did I end up modeling it and get an answer and so forth? And what I had to do, now maybe somebody else wouldn't have had to, but certainly the guy I was doing it for, he couldn't do it at all. He wasn't coming up with a model at all. What I had to do was first think of it as a network kind of thing, a staged process where I drew arrows and all that, and then I turned it into a linear program. And so that's part of the reason why, why are we looking at networks? Well, because your project uses a network, and so it'd be nice to kind of get some idea of why I might have ever tried that. Well, because there are all these nice network models that can be turned into linear programs. Okie doke. I will see you next Friday. And then I'll probably be sending out some email, because it's the Monday after that, after next Friday. So a week from this Monday, a week from next Friday that I won't be here. So what we might want to do is meet the Monday that week. So we might want to meet Friday and then Monday.
Okay.
But I'll send out some emails and we'll chat about it on email.